climate is really the temperature of our planet, and it's both natural, it's due to natural things like the sun and our orbital mechanics. It's also due to human activities, our production of greenhouse gases. And to understand climate, you can't think of just natural or human. You have to be able to understand both of those things and how they come together, how they play off of each other, thereby relating to not only the temperature of the planet, but other aspects, cloudiness, life on the planet, precipitation. All of these things are tied up in our climate history.
Welcome to Superheroes of Science. I'm Stephen.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support. Back with us today on Superheroes of Science, we have Dan Cziczo. Dan is the department head and professor in the Department of Earth, Atmospheric, and Planetary Sciences here at Purdue University. And Dan, you've been a guest a couple times, and we're so pleased to welcome you back.
Thank you so much for having me back. It was really exciting to be here, and I'm really looking forward to talking about climate and climate change today with you both.
Oh, we definitely appreciate it. A lot of schools we go to, and a lot of teachers we talk to, there's just a lot of people don't quite understand, and it's kind of makes sense to bring on an atmospheric scientist to explain, so we have a better understanding of what really is climate change. What does that mean?
This is one of my favorite things about science, actually, is sort of the merging of science and history, because I think what we're going to talk about today is really the history behind climate change. I think very often we sort of think about this as being a modern thing or a modern debate. And it actually can't be further from the truth. It's something that as scientists we've been doing for well over 150 years now, thinking about climate change, how we can affect the world around us. And so I think it'll be really fun to have that conversation with you both today.
Well, awesome.
All right. Well, again, I'm really glad to be here with you today. And what we talked about in preparing for this was just to go over sort of the history of climate and why our current climate is what it is. And so I just wanted to start this out with my favorite quote, which is, "Those who cannot remember the past are condemned to repeat it." And this was by George Santayana. And I think it's a really beautiful jumping off point, because when you talk about climate, you really have to talk about the climate history of the planet. And so I think our first slide is really important to do this one, which is almost a million-year record of the climate of the planet. So on the x-axis here, we have time into the past, starting at zero. You can think about zero as essentially being the current day, going back 800,000 years. And then on the y-axis over here, we've got this really nice temperature scale. And one of the things that you can see here is that it's a relative scale, and so we're going to talk about the current day being sort of a zero value, and we'll talk more about that in a moment. But you can see that the Earth has actually been considerably warmer and considerably colder in the past. And so I think this is something that a lot of us learn as grade schoolers, is that there's these very cold past periods, and we call these typically ice ages, and we sort of think about mammoths roaming around on the planet. And you can see there's a number of those in this 800,000 year record. What's interesting is that there's also these warmer periods, and as scientists, we tend to call these interstitial periods. And many years ago, 100 years ago now, people really saw that there was sort of a periodicity to this, or a heartbeat is what some call it, of this climate, this sort of warm period, cold period, warm period, cold period. And the scientist that we think of that really worked this out is Milankovitch. And again, he did this 100 years ago. This was 1920 that he really figured out this periodicity. But before we get to that, I just wanted to mention a few things here, because this idea of sort of 0 years starting in the modern day, and this idea of a temperature anomaly, sort of a difference in temperature from the modern day, might be hard for somebody that's just listening to this. And so I wanted to set the stage for this and just say, this as scientists is our way of sort of thinking about the world around us. We have to sort of set a 0 point. And so we have to sort of think about there being, a concept of a climate, and where do we start from? It has to be colder or warmer than that. It's sometimes too abstract to think in terms of, degrees. And so this idea that there's an average temperature, really started, several decades ago. And this can be any date that we really want it to be. Some people use the year 2000 climate. Some people use the year 1950. Some people use the year 1750, and you'll see some of those as we talk today. So there's different 0 points, and we'll try to be clear about that. But the idea is to sort of, talk about things in relative terms and not absolute terms. And the same thing goes for the year on here. So using this 00 really kind of implies like we're talking about a climate change and a temperature change from some period that we can all relate to. Might be something in our lifetime, our grandparents' lifetime, or 1750. That's often picked out as sort of the start of the Industrial Revolution.
Now, I understand that, to my understanding, I'll say that you're 800,000 years ago. I mean, it's a long time, and I haven't seen any books that old. And so how do we know what the temperature was that long ago?
Yeah, Stephen, this is one of the reasons I love joining you and Sarah is that you guys always ask the best questions. So that's a great one. It's like, how do we develop a record like this? And the answer to that is that we have to use something called proxies. And proxies are other ways of measuring temperature. We'll talk about it on the next slide or a couple slides from now that, we've only really had thermometers for about 150 years now in a variety of locations. And there wasn't somebody running around a million years ago with a thermometer. So what do we do? One of the reasons that this is 800,000 years old is that we have really good proxies going back about that long. And one of them is ice cores that we can date back that far. So we can date the ice cores by layers in them, isotopes in them, things like volcanic emissions, volcanic ash in them. And we can go back this far and say with high certainty, within a few years of the time. And then what we can do is we can pick out things in those ice cores, whether they be trapped bubbles of air or some of these particulates that are in there. And we can get proxies for temperature so we can develop something like this. The other thing is that, we can work with our colleagues that are in paleontology, and they have certain fossil records, fossils that might only exist at certain temperature ranges that allow us to pin down global temperatures with a high degree of accuracy. And so when you see a record like this, this green color on here, this is all proxies. And the shading that you can see here is the uncertainty. And so you're seeing uncertainties of, something on the order of about a degree plus or minus. Sometimes you've got enough proxies or you've got a high degree of certainty, you can shrink it down to a few tenths of a degree of uncertainty. But that's a great question. And that's how you develop something like this. People might be familiar, from their own backyard with cutting down trees and looking at tree rings, and how well a tree grows often correlates with temperature. So in the more modern age where we even have trees, we can develop even better proxies. But for something like this, it's largely ice cores and fossils. So, one of the things that we just talked about was Milankovitch, and he was an incredible scientist, and he's the first one that came up with this idea that the climate of the past had this sort of heartbeat or this periodicity, and he realized that this had to do with orbital mechanics. And so, what do we mean by that? It's not sending spacecraft to different planets, which is how we think of orbital mechanics nowadays. And you guys have done some great interviews on that. This really has to do with the orbital mechanics of the Earth. And so, we don't often think about this because the timescales are so long, but the Earth actually moves around the sun in different ways. The sort of eccentricity, that sort of ellipse that we move around in can become sort of fatter, longer, or more squat. And that changes how much solar energy is reaching the planet. The tilt of our axis can change, sort of like a top that's precession. The northern hemisphere can kind of tilt over more towards the sun or further away from the sun year after year. And so it's pretty amazing to think, but over 100 years ago, without a computer, Milankovitch was able to work this out. The time scales for all of these things to take place, and time scales I've highlighted here in red because that's going to be one of the themes that we're going to go over. But again, I just want to sort of set the stage here that we're talking about time scales in thousands of years. And so again, this is a modern representation of what Milankovitch did 100 plus years ago. But he worked out, sort of what the periodicity of the tilt looked like, the eccentricity of the orbit, some of these other orbital parameters. And what he was able to do was essentially add all of these things together. And again, I'm just constantly amazed. He did this in an era without computers. So this was all essentially hand calculations. And he came up with this concept of daily insolation, or came up with a value of daily insolation. How much energy was the planet receiving? And what's pretty cool here is that you can see that, the year zero, again, is this arbitrary number. And when Milankovitch did this, year zero would have been 1920. And so he was able to plot negative numbers. What was it that the Earth was experiencing in the past? But he was also able to predict climate into the future based on orbital mechanics, because he knew what these certain orbital parameters should be doing into the future. And so you asked the great question about these proxies, or how we develop temperature. This was done by other researchers later, but they were actually able to match up these different temperature scales in the past. The future ones haven't been developed yet, but they were able to match those up. And you can see this really beautiful correlation of these interstitial periods and these ice ages with the Milankovitch cycles and this amount of energy that the planet is receiving.
When you say they were able to match up, is it something they were trying to do, or is that something that they produced their data and it did happen to match up?
Yeah, I think a little bit of both. I mean, that's one of the ways that science works, right? So this is the scientific method that we all sort of learn about early in high school, is that, you come up with a theory. So that's the idea. So I think the theory was that the data should match this insulation or these orbital mechanics that Milankovitch had worked out. But then you have to actually do the data and try to match them up. And so this is a case where sort of the theory and the data matched up. And then we're able to take it, further steps. And those are the things that we're going to talk about in a few moments, is when they don't match up, which gets really, really interesting. So if we want to think about this a little bit further, there's some good news here, which everybody should be happy about, which is that we're in what we call an interstitial period now. I know today in West Lafayette, we had our first frost. So it's sometimes hard to think about this being a warm period of the climate. But the average temperature of the planet right now is 57 Fahrenheit, which is about 14 degrees centigrade. And that's pretty nice and warm. We still have polar caps, so there's cold areas, the Arctic and the Antarctic. But by and large, it's a pretty warm climate. We're certainly not in an ice age. We don't have these massive ice sheets over North America and parts of Europe and Siberia like we would have during an ice age. So this is good news. But what we're really concerned about today, or what we really want to talk about, is not this 800,000 year record, but maybe a much smaller record, measured in some thousands of years. And so let's talk about that. And so this is a much more modern record, and we've changed that x-axis here now. So we've gone into our calendar years that we sort of think about. So the year 2000 is one of the final years on the record here, and we'll talk about that sort of data that's going to be over there in a few moments. And we're going to go back to about the year 500. So if we're thinking about history, maybe towards the end of the Roman Empire or something like that. And again, we don't have modern thermometers for this part of the record. So we have to use these proxies. We can use those ice cores. Now we can start using things like tree rings. And one thing that the viewers are going to see right away is that the y-axis now is not plus or minus 8 degrees centigrade. Now it's just plus or minus 0.5 degrees centigrade. A little bit colder period, so you can see it's going down to -1 +5. And so one of the first points we want to make is that we as humans, anatomically modern humans have been around for a long time, but civilization hasn't. And our civilization has really evolved in a very stable climate. And so if we think about, the last 2,000 years or so, we're talking about changes that have only been a few tenths of a degree, not these massive swings like ice ages, -5, -8, +2, +4. And that's allowed us to adapt ourselves and really adapt the world around us to our needs. So you can see that there are warm and cold periods within this record, but they're not like these interstitial periods in these ice ages. There was a period of time of great prosperity in the Middle Ages, and that was called the medieval warm period. And you can see here it was just a few tenths of a degree warmer than the period that preceded it. There's also cold periods. There's something that folks will probably have heard of called the Little Ice Age that was in, sort of the 15, 16, 1700s, parts of those years. And then there's dips in temperature that are rather rapid. And these tend to be volcanic eruptions where a lot of material was thrown into the sky. Talk about this more later. And the sun was actually blotted out to some extent. The last major one that we have, some of us will remember Pinatubo in the 1990s, when the temperature of the planet for a few years went down by a few tenths of a degree. But you can see that in the record. But again, the point to really hammer home is that civilization as we know it did not evolve with major temperature swings. In fact, we think about periods of prosperity and periods of famine being really related to a few tenths of a degree change, not these massive climatic swings that we saw because of orbital mechanics. And so just to sort of close out this slide, we can sort of ask, well, what's been happening, in the last few decades, the lifetime of the people that are viewing this. And that's really interesting because now we have this really rapid temperature rise. And so this part of the trace here, this blue part, is the part that we as scientists talk about as being the instrumental record. And what we mean by this is these are the direct measurements of temperature. This is when we've had not only accurate thermometers, but also enough accurate thermometers around the planet that we can talk about what the global temperature is. If you got one thermometer, it's great. You can get the temperature in one location. But if you don't have it around the planet, you can't say anything about sort of global climate. You can just say about temperature in my location. So in about 1880, we had enough thermometers in different places that allowed us to do a global temperature. And that kind of followed this flat trend for a while. And then we started to see this sort of radical uptick that you can see has no precedent otherwise in this record over the last few thousand years. And then going back to our word of the day, timescale, you can also see that this is not orbital mechanics. That's thousands of years. This is a rapid change in temperature by over a degree in just a few decades. And so now we have to start thinking about what else might have happened here that would explain this. All right, so moving on, one of the things that we might think about explaining this are correlations. And so, Stephen, this kind of goes back to your point earlier about, what is it that's causing something? And often you develop a theory about what that is, and then you try to prove it. And sometimes you have a bit of evidence. And so I'm going to tell this story a little bit backwards. I'll tell you about the people that sort of developed the theory. But first, I want to tell you about some of the correlations that are seen in these temperature records over a long period of time. And one of the things that we see that's often involved as a participant in climate beyond just orbital mechanics is actually carbon dioxide, what we now call a greenhouse gas. And so the first thing that we'd like people to understand is that carbon dioxide has always been in our atmosphere. It's just part of the atmosphere as a whole. It comes from a variety of sources that we'll talk about later. It can be natural from the planet itself. It can be something that comes out of volcanic emissions, but it can also be part of the cycle of life, the carbon cycle, part of photosynthesis and respiration from plants as well as from animals, breathing out. But we can look at this CO2 concentration over time, and this is really interesting. And again, this is the sort of natural sort of link between carbon dioxide and temperature. And so using these proxies, what you can see is that carbon dioxide can vary widely. We use this number of parts per million in the atmosphere. If we grab a million molecules, how many of them are CO2? And you can see that about 280 during these interstitial periods are carbon dioxide. And during these very cold periods, many less molecules, about 100, 180 are carbon dioxide. And you can see this beautiful link with temperature. And in this case, this is Antarctic temperature from one of those ice core records. And you can see this link. And so now, one might ask, well, is this cause or is this effect? Are both things, just participating? Or are they being forced by something else, like these orbital mechanics? Or is there something else that's going on? And what's interesting about this, again, going back to sort of the history of the science, is that this is not a modern question. This isn't something that we're trying to work out now. How do greenhouse gases participate in our global climate? This predates, talk about human impacts on climate change, just going back to basic science. And so this is this is a really famous scientist from the 1800s, John Tyndall. And so John Tyndall was from the UK. And he's particularly close to my heart because he was an experimentalist like I am. And so he built things in the lab to do measurements, to investigate. And he built this device that he called a comparative spectrometer. And you can see here that essentially it was this big tube, and he was able to fill the tube with whatever he wanted to, different gases. And then he was able to pass different light sources across it. And so these could be, sort of infrared, visible, or ultraviolet. And then he was able to see what that gas did with that material. And so he did some really, really interesting studies. And one of the things that he found was that, although the atmosphere is mostly made out of nitrogen and oxygen, he wasn't able to get those to do much in his comparative spectrometer. But he went a little bit further, and he found out that there were certain sort of trace substances in the atmosphere, and carbon dioxide is the big one that we were just talking about, that when he put them in there, they were able to participate with some of these types of light. And so, for example, he was able to find that, CO2 would absorb things like infrared radiation. It would trap it and then re-radiate it. And so we now call these greenhouse gases, but it's this idea that, they act as sort of a blanket around the planet, that as the planet is trying to give off heat into space, that you have these materials that trap that energy, and some of it is let go into space, but some of it is re-radiated down towards the planet. And they actually act, again, as a blanket or a greenhouse, keeping the planet warmer than it would otherwise be. And so I thought this was really fascinating work. Another great story from this time is that he had a contemporary in the United States, actually in Massachusetts. Her name was Eunice Foote. And so Eunice and John were doing very much the same experiments at the same time. It's clear that they probably knew about each other's work through the scientific community, but they were acting very much independently and coming up with the same findings. For many years, we really sort of said that John Tyndall did this work. And more recently, we've realized that Eunice Foote really discovered it at the same time. This is one of these issues of women in science before the modern age, that she was actually not allowed to present her findings at scientific conferences in that day, and instead had to designate a man to present her research. So she did outstanding scientific research, and perhaps didn't pick the right guy to go and present these results, and was therefore not able to get the traction scientifically that John Tyndall was. And there was a really nice article in the New York Times a few years ago that sort of really sort of rediscovers the life of Eunice Foote and how important she was for our modern understanding of greenhouse gases.
Tyndall I've heard of.
Yeah. Not the other. Thank you. That was very interesting.
Look up Eunice Foote. It's amazing what she was able to do. Really the same type of work, and actually expanded upon some of Tyndall's results as well, or did more than he did. So, now we get into this interesting issue, which is carbon dioxide itself, right? Again, as we mentioned earlier, carbon dioxide is completely natural. It's been around as long as the Earth has. We see it around other bodies. Other planets have atmospheres of carbon dioxide, like Mars and Venus. And so CO2 was here long before humans. And there was this, really intricate cycle of CO2 in our climate. It's not to take away from orbital mechanics, which is the big driver of these climate cycles, but CO2 is absolutely there in the background as well. And so you could think about this CO2 effect on climate that's playing out, over the orbital mechanics, where you would increase CO2. So perhaps you'd have, volcanic emissions. CO2 in the atmosphere would go up. You could imagine that would lead to a warmer planet. There's then ways of removing CO2. There's weathering of minerals, silicates. You can then tie that carbon up in things like calcium carbonate, CaCO3, which would sediment out and be buried. And then the CO2 would go down over a period of time, waiting for another volcano to erupt and so on. And so what's really interesting about this is that, you can think about these radically different Earths. And so this is not one that we have a picture from space of, but this is an image that NASA developed called Snowball Earth. And we believe there were two such periods in sort of the deep past, where the Earth was in one of these ice ages because of orbital mechanics, but you also had very low CO2 that compounded this. And so you had very low insulation, very low energy reaching the planet. And at the same time, you had very few of these greenhouse gases. Maybe volcanoes just hadn't been going off randomly for a long period of time. And the Earth not only went into an ice age, but it actually became almost completely frozen. And this only was a system that you could break out of if you had enough volcanic eruptions pumping CO2 back into the atmosphere to warm the planet up. Because you can see in a case like this, there's not a whole lot of sunlight making it to the planet. It's the whole planet is covered with snow, and that sunlight's being reflected back into space. Be sort of like an endless winter, even at the equatorial regions. But we did break out of it. We broke out of these, probably 2 different times. But it really highlights this power of CO2, not only to allow the planet to get colder if there's not enough, but also to create the planet getting much warmer and breaking out of these snowball states. So just a visual representation of this is this idea of again, timescale. So, when we think about weathering, we think about volcanic eruptions, we think about sequestration of CO2 falling out as calcium carbonate, the C in calcium carbonate. Orbital mechanics, thousands of years. These type of processes, these are geological processes. So again, we're talking about millions of years here. And so this is sort of superimposed. It's even another time scale on those orbital time scales of, removing that CO2, sequestering it back into some type of sediment, and then maybe recharging the CO2 in the atmosphere naturally. So again, just for people to put this into perspective, we're talking about, thousands to millions of years for these natural climate timescales. Let's move on and start thinking about this from a human sense. And for history, again, our viewers probably are thinking about this as things that they learned in history class. And one thing that we probably all learned about in grade school was the Industrial Revolution. So this was this idea that at some point in time, and pick out a year, sometime in the 1700s, 1750 is often chosen as the beginning of the Industrial Revolution. We as humans really sort of developed these technologies really based around a carbon sort of fuel infrastructure. At first, this was probably burning of wood, large forests being burned. And later this became things like coal and then oil and in more recent times, even natural gas and things like that. But again, a carbon fuel source being combusted, the generation of CO2. And so I really like this figure. It comes from the Intergovernmental Panel on Climate Change, their 5th report, which they call AR5. And this was something that looked at the emission of greenhouse gases really since the beginning of the Industrial Revolution. But I like this figure because it started in 1970, which happens to coincide with me being born. And you can see this not only increased the amount that was being emitted, 51 years ago, but the increase that we've seen over time. So, the Industrial Revolution was really the beginning of this. And you can imagine that, really there was some combustion going on before then. That was really when it started to ramp up. And so by 1970, so for that few 100-year period, you can see that at that point, we were emitting something like 27 gigatons of carbon to the atmosphere in the form of CO2 on an annual basis. And every year since then, that has increased. So by 1990, this was up to 38 gigatons. By 2010, the last time that we have a really good assessment, we're up to almost 50 gigatons. So, you're talking about almost a factor of 2 increase just between the year I was born and a few years ago, about a decade ago now. So if we think about this, now it's where the wheels are spinning in all of our heads, right? So Tyndall and Eunice Foote have worked out the fact that CO2 is a greenhouse gas. We're talking about that these greenhouse gases being emitted because of human activities to the atmosphere. And so the first question we might say is, well, we're emitting this amount, and maybe 50 gigatons is an abstract amount, but can we really see it in the Earth system? And so this is a beautiful plot that's sometimes called a Keeling curve, and we'll talk about that in a few moments. But this is the amount of carbon dioxide in the atmosphere versus years. And you can see this record is really starting in the 1950s. So let's stop here and talk a little bit about this. A few things that are going to come to mind. The first one is that, we talked about these ice cores and finding these little bubbles in them and looking at how much CO2 is in them earlier and saying it was about 280 parts per million. But now this gets a little weird, right? Because I'm starting a curve here in the 1950s that's already at about 310 parts per million. And so what's going on? Well, between those intervening years, from the beginning of the Industrial Revolution until this measurement started, in this case in the 1950s, the carbon dioxide in the atmosphere had already increased because of human emissions. We missed that in this record. It was already there. The other thing that we should see here is that this carbon dioxide is increasing every year. And you wouldn't be surprised to think that this trend mimics that trend of emissions that we were looking at on the last slide. And so by the early years of the 2010s, the teens, we had gone from 280 pre-industrial revolution to over 400 parts per million. So something like a 50% almost increase in carbon dioxide. The other thing that you can see is that every year has this sort of up, down. And so what is this? Well, this is the natural CO2 in the background. This is sort of plant photosynthesis and respiration going on, much more land area, many more plants in the Northern Hemisphere. So Northern Hemisphere summers, you have a lot of CO2 being taken up and formed into plant mass, and then a loss of that material, respiration, and photosynthesis going on in the Southern Hemisphere during the Northern Hemisphere winter. So increase, decrease, increase, decrease. So that's the natural cycle. But in a pre-industrial world, that should happen on the same baseline of about 280. Instead, we are superimposing this increase because of human activities onto it. And so that's what we see here. I also use this name for it, Keeling. And so where does Keeling come from? Well, Keeling was a scientist that first put one of these modern CO2 monitors out there. He did this on the top of Mauna Loa in Hawaii, a famous observatory there. And what was he trying to do? Well, he was just trying to measure CO2. And at the time, he really thought that, this would be a flat record and he might see this sort of annual variability. But it only took him a few years to sort of scratch his head and realize he was seeing CO2 go up. And he very quickly put together the fact that this was an increase that wasn't natural. It was instead due to human activities. And even though he was in this very remote site in this very high altitude observatory in Hawaii, this was carbon dioxide from human sources all over the planet, mixing in the atmosphere and leading to an increase of this greenhouse gas.
It's kind of disappointing that he was surprised, but we think about how many people are out there doing things in factories, industry. I guess it shouldn't be surprising in retrospect.
Yeah, it's a great point, Stephen. Hindsight is always 2020, and we'll actually talk more about that in just a few moments. So I wanted to finish this slide by just putting a quick quote up from that Intergovernmental Panel on Climate Change report. And so one of the things that they pointed out in this, from the use of things like Keeling curves and looking at other greenhouse gases, some of the things that Tyndall and Foote looked at, is that the concentration of carbon dioxide, methane, nitrous oxide, and others are unprecedented in this 800,000 year record that we have from these ice core data. So not only are we seeing, this sort of natural cycle in the background, but it's saying that we as humans have impacted the atmosphere so greatly that we've broken out of any sort of natural historic record. So, you can think of a small emission of carbon dioxide to the atmosphere maybe being within the natural bounds. That's no longer the case, and it hasn't been for a long time. And so we really are at these unprecedented levels. We've really created a planetary atmosphere around the Earth that has no natural sort of case that we know of. We're well outside of that. And so I just want to make the point here now again about timescales, which is this idea that humans are participating in the atmosphere, that we're making things and leading to an unprecedented atmosphere, has a timescale of its own. We're talking again about the Industrial Revolution being a couple hundred years ago, and we're talking about changes of an order of 2 or 3 in my 50-year lifetime. And so you're now talking about changes that can have an impact on climate that are measured in decades or perhaps even years. This increase in CO2 and this Keeling curve of increase in carbon dioxide, increase in greenhouse gases. And so now we're starting to think about that curve we saw earlier, where we saw these ice ages and interstitial periods separated by tens of thousands of years, maybe other things that are taking 1,000 years to change, long-term geological processes, 1 million years. Well, now we're seeing a timescale because of humans of decades. And so now we're putting into perspective that increase of a degree or more that we've seen over a few decades. That's the human impact on climate. So again, you have these natural CO2 processes, these natural orbital mechanics processes, and now you're starting to superimpose the human impact on top of that. And that's what that recent modern temperature rise is due to.
And this can be determined because we're taking readings and we have a record of this, and we were able, and that's why we can say these things, right? Because we're scientists, we've collected this data.
Absolutely right, Sarah. Yeah, no, that's exactly right. So these are direct measurements. Again, it's this thing that we often call the instrumental record, but we're making these measurements. And so for this modern period, we're not even using proxies anymore. Key-leaning is directly measuring CO2. Scientists are measuring temperature. So now we've really worked out all the fundamentals of this. We really understand the nuts and bolts. We'll get into some of the uncertainty in a few moments, but you're absolutely right. So I just sort of love the history of this. And so here's another character in sort of the climate story, and his name is Svante Arrhenius. And he was around sort of middle 1800s to the early 1900s. So after Tyndall and Foote, and he's really going to expound on their work. So he's going to take their data and he's going to work it into sort of climate models, if we can call them those very early climate models, perhaps the earliest climate model in some sense. And so a great quote that he had is, if the quantity of carbonic acid, which was his name for CO2 or the name at the time, increases in geometric progression, the augmentation of the temperature will increase nearly in arithmetic progression. And so what he's talking about is sort of the form and the increase in temperature of the planet due to an increase in CO2. And so in the very late 1800s, Arrhenius worked out what we now call climate sensitivity. He asked himself, well, what if you double CO2? And so remember, at that time, it was very early in the Industrial Revolution. So CO2 is still around 280 parts per million, maybe 290 parts per million. And so he doubles that, and he finds that the climate should warm because of this increase in greenhouse gases by about 5.5 degrees. And here's a lesson that I always talk to my students about, which is that Arrhenius published this in a paper, which was great. And then he published a second paper later, and he revised this down to 4 degrees because he found he had a math error in the first paper. And so I always tell my students, don't publish 2 papers. Make sure you don't make a mistake in the first one. Nonetheless, Arrhenius figured this out, and he came up with this idea of climate sensitivity, a doubling in CO2 leading to a 4-degree increase. And I love this part about it, but Arrhenius was not trying to do this because he was thinking about climate change in the future. He wasn't worried about global warming, the term that we use in the modern sense. He was actually thinking about it in a completely different way. Svante Arrhenius was from Scandinavia, and he felt that the climate of Scandinavia, then in the late 1800s, was far too cold. And he looked south and he saw the breadbasket of Europe being in, sort of modern Germany and France and places like that. And what he wanted to do was he wanted to find a way to increase the temperature in Scandinavia to move the breadbasket of Europe north into the place that he was. And so he actually wrote about lighting the coal fields of Europe on fire to augment CO2 so that he could warm the climate and basically create a warmer climate where he was at. It doesn't seem like it ever occurred to him that this would have impacts on people further south. He was very much, I guess, a homer in that sense. He was only thinking about the impact on him, his country, his region, and so on.
Wow.
Yeah, no, Svante was quite a character. So to start wrapping this part of the talk up, we can talk about some of the uncertainty in a moment. I wanted to just sort of give the viewers a perspective on this and the timescales we're talking about. I don't want to leave anybody with the impression that, if we turn off the CO2 taps tomorrow, the climate is just going to go back to that pre-industrial state. That's just simply not the case. CO2 itself has a lifetime in the atmosphere, and the impacts of CO2 have a lifetime, and some of the warming that we see has a lifetime. And so this is a really nice paper that came out from Susan Solomon and others in the Proceedings of the National Academy of Science, one of the premier journals about 10 years ago now. And so what Susan pointed out in this was that, this is one scenario where CO2 continues to rise until about the year 2050, and that's the dashed line here. And then, we as a society start to really get our act together, and we can really start drawing down that CO2. And you'll note the Y scale on here just goes to 1. It's normalized. It says, CO2 goes to some level, pick whatever number you want, 600 parts per million, whatever it is. But we get to some point. And then what we can think about is that there's some warming effects from that CO2. And because the CO2 is being produced and getting into the climate system and then becoming a player as a greenhouse gas, there's chemistry involved, there's radiative effects that are involved. And so you have this lag. And so what you see is that when you emit CO2, it's not immediate. It's not that day that you see you see some of the effects, but some of them lag behind. And so even when you start turning the taps off, it is some years later that you actually see the impact of what you did at an earlier point in time. The other thing is that you see that even though we start turning off the taps on a certain day, that there's a time lag, there's a removal time, the lifetime of CO2. And so, in this case, even though you're dropping these down, you're seeing effects still continuing for some hundreds of years afterwards. So, taps go off again, something like in 2050, but you're still seeing impacts of this historic CO2 that was putting into the atmosphere hundreds of years later. And then it also has to be brought up that once you've warmed the planet, it doesn't cool down right away. For the viewers, just go home, put a pan into your oven and then take it out. You're not going to grab that pan immediately afterwards. That pan has to take some time to cool off. And the same thing goes for the planet. And this is especially true of our oceans. Once you warm the oceans up, that's a lot of energy you've put into that. And that's going to take a lot of time to cool down. So again, you put this material in, the CO2 or the greenhouse gases in, you don't lose that energy overnight. It takes hundreds of years. So we're really not talking about what we're doing today impacting our kids and our grandkids. We're talking about impacting our great grandkids in the end. And so, this is something that we can talk about solutions to this in a few moments, but I really want to hammer home this point that this is not something that's going to go away tomorrow, even if we find a way to decarbonize our economy.
Very fair statement.
Yeah.
It makes it harder to care sometimes if you can't see, I won't see the impact of my actions. It makes it harder for people, I think, to think, it's not worth doing.
No, it's really true. It's another one of my favorite quotes, Stephen, is this old proverb about societies grow great when old men plant trees that they'll never sit under. And I probably butchered the quote, but you get the idea is that you really have to be forward thinking. You have to be doing things for future generations. If you're only thinking about impacts on us, you're never going to decarbonize an economy. You're never going to move to alternative energy technologies at that point. And that's really what we have to be thinking about is the impacts 100 years from now or 1,000 years from now. Okay, so for the last part of what we really want to go over, I think today, I did want to talk a little bit about uncertainty, and some of the modern things that we as scientists are working on. And so, we've already established what's shown here. So this is a map of the world and sort of a temperature change between the year 1900 and the year 2012. So about 10 years ago, again, this is a really, well put together record. We can't develop these overnight. So that's why there's often a lag in the plots that I show. So again, acknowledge that in about 1880, we had really good temperature records for the globe in general. And we can now say with a very, very high degree of certainty that the planet is warmer, more than a degree centigrade warmer, more than 1.5 degrees warmer over land since that time. Again, that was a time when CO2 was, something around 280 parts per million. It's now well over 400 parts per million. And so these two things are tracking. And so if we think about the 20 warmest years on record, you can see here there's this litany from the 20 teens moving downward. You can see a few 1990s on there. So I'm gonna stop here because I want to tell a quick story. The first one is when I first started doing climate work, there were some years from the 1930s that were on this list. And we often think in America about the Dust Bowl, these horrendous years during the Great Depression and the great famines that we saw, human migration, things like that. Those were very warm years. but they are nothing like the last 2 decades. The other thing is that, there's a bit of a lag again in getting data. And so what we can say is that 2020 is now tied for first. And so that means one of these years, even from the 1990s, like a reverse Pez dispenser has been popped off the bottom of this list, replaced by a year on record. We haven't finished 2021 at this point, but right now, 2021 is on track to be number one, meaning that 2020 becomes number two with 2016, and we dropped 1995 off the list. And so when I started this, there were some 1930s on here. Very soon, there's not going to be the 1990s on here. And so whenever anybody asks me about, how are we going to be in a future climate, I tell them we're in a different climate now. The climate that I was born into in 1970 is not the climate we have on the planet now. We are living in a new climate state, and one that's really unprecedented again in this long series of time, certainly outside of what our civilization, the last several thousand years have evolved in.
Well, I think this is probably a hypothetical question. Well, I think it's your best guess question. We'll put it that way. But if we're on track to be the warmest in 2020, what is right now the warmest on record, but we had like a global shutdown that happened. And so when will we see a slight dip from that shutdown? I mean, as you pointed out previous slides, there is a lag in what happens in the system. And so are we expecting to see where it'll level off or even dip because of that shutdown?
Yeah, Stephen, another great question. So we've actually seen the dip, again, to Sarah's earlier point, in the instrumental record. So, when we monitor atmospheric CO2, again, this expansion of this Keeling curve, we actually saw the slowdown, a couple of slowdowns within, our lifetimes. When the Soviet Union fell in the late 1980s and early 1990s, locally speaking, we could see that change in industry when their economy collapsed and essentially overnight. In a regional sense, we were able to see that, and that's in the instrumental record. The so-called Great Recession in the late aughts, 2008 and so on, we were able to see that in a slowdown in industry. CO2, didn't stop for a period of time. That curve, the curve of increase, flattened out and actually went down for a short while. And then last year, the impact from COVID, when a lot of us were sort of, working from home and so on, cars weren't running, industry wasn't running at 100% capacity. We saw the curve tilt over in CO2 emissions. We haven't seen a temperature implication for that, probably because these lags, as you said, in the time system. I would actually be surprised if we really see like a temperature regression or a cooling. What we might just not see is a big increase for a year or something like that. But again, we're locked into these past trends, and we have this sort of, impact over years and ocean heating. So, 1 year effects from humans, a shutdown or a slowdown, probably isn't going to radically alter this. Maybe you'll get the number 5 year of warming as opposed to the number 1 year of warming. But I think that's the only type of impact you would see. So to sort of sum this big part of the talk, really the meat and potatoes of what we wanted to talk about, I just want to hammer home again the point that temperature now is greater than it has been in thousands of years, really within civilization's time span. The other thing is that I did want to bring up the climate sensitivity, and Arrhenius came up with this idea of about a 4-degree increase for a doubling of CO2. Where are we at right now? We're just a little bit under a 50% increase in CO2 since pre-industrial times. Arrhenius would say that we should have seen about 1.7 degrees of warming, and yet we said that we only saw something a little bit over a degree of warming. So I think we want to talk about that in terms of uncertainty for just a couple minutes. But I will just sum up this part. This is a Cliff Notes version of what we're doing. So really, the big take-home message is greenhouse gases, predominantly CO2, warm Earth because they're trapping this heat that the planet's trying to give off. It's like throwing a blanket on top of us on a cold night. It's going to warm us up. Blanket doesn't produce heat. It just traps our heat. That's what's going on. And then the other thing is that I really want to hammer home this point that, the basic understanding of greenhouse gases, planetary climate, this is not new. It's not something we did last year, a decade ago. This has been around since the 1800s. The basics really developed in the 1850s and then expanded on by the late 1890s. We really understood probably 2/3 of climate change, even at just that point. So we mentioned that climate sensitivity hasn't exactly matched up, and there's still this discrepancy and this uncertainty. And I did want to talk about this, and this is very selfish and self-serving because this is my research. This is what we do in our group. And so I love this picture. This is something that I had on my wall as a kid, and this actually came out of the Japanese Space Agency. This is a real image of the Earth, but it's one that was stitched together in mosaic. They took certain shots from certain locations at certain times of day, and they were able to knit this together. And you can see this, beautiful image of North America and South America here, a little bit of Africa, Europe, and Asia at the very top. And so I'm just going to ask you to, this is a beautiful picture of the Earth, but when they did the mosaic, what were they intentionally not doing?
Holes.
Yeah, they missed out. They did it at a season, so there was no sea ice.
Oh.
Yeah, what else did they do? Anything else missing that might be outside today?
Missing?
Yeah.
Mercy. It might be outside today. Oh, you mean like it's all daytime?
Yeah.
It is all daytime. But thinking about clouds.
Oh, okay.
So
that's what.
Yeah, isn't it great? I mean, you don't even think about it when you look at this image, right? It's like, oh, it's beautiful. Like, what a great day. But what they missed out on is that any one time, something like 50%, a third to a half of the globe can be covered in clouds. And so now you can see the sea ice here up in the northern hemisphere. You can also see these beautiful cloud systems around the planet. And one of the things that we realized when it comes to clouds, and this is something that Arrhenius didn't take into account, was that not all of the solar energy makes it to the surface, and not all of that energy just makes it back out into space. Instead, there's this layer of something over the planet. In this case, these very white, these very bright clouds that can reflect sunlight back into space. And to a lesser extent, they can actually participate in trapping some of that heat, trying to make it out, a lesser impact from that. So when we think about these things in the Earth system, and I mentioned clouds, but I should also talk about the thing that causes clouds, which are small particles in the atmosphere, something that we call aerosols, which I think you guys both did a great presentation on at Superheroes of Science just a week or so ago. These particles are big players in the climate system in a way that we don't often think of. And so I love this image. This is San Francisco last year during the wildfires. I don't love it from the sense that, wildfires were going on. But I love this idea of this is a daytime picture, but there's so many particles in the atmosphere that they've not only turned on the streetlights, but you can see that you don't have sort of the perception of what's going on here. You don't have sort of the optical clarity of what you would have during a normal day. And the reason is that there's these wildfire particles, and these folks are wearing masks. Of course, this is during COVID, but there's also this health effect of so many particles. But you can really make the point here that the sun is out above this particulate layer. It should be making it down to the surface, but instead these particles are scattering so much light that not enough light is making it down to really see clearly, so much so that the streetlights are on. And you have to ask, well, what happened to that sunlight? Well, a lot of it might have been absorbed by the particles, but also scattered back into space. And again, going back a couple of slides, that's what's really happening with these clouds here, is that you can see them as bright white because the sunlight that would otherwise be making it to the surface is scattering off the clouds and coming back towards the observer. In this case, the satellite. In this case, it's the photographer that scattering is taking place. So we call this the direct effect of particles on climate. And you can think of this idea that if you put more of certain kinds of particles into the climate system, you're not going to trap heat. You're going to actually scatter sunlight back into space. You're going to cool the climate. And this is the first reason why Arrhenius wasn't entirely right, was that he wasn't thinking of particles and clouds being in the climate system. So when we think about clouds, you can ask yourself, well, maybe clouds haven't changed at all. Maybe they were exactly the same in the year 1750 as they are now. And that's actually not the case. And so these are two images that came out of NASA. These are sort of conceptual images. But this is a so-called pre-industrial cloud. And so you can think about a pre-industrial atmosphere. It had less CO2, but it also had less particles, less things that were put there by humans, probably by a factor of 2 or more from what we now know, about twice as many particles in the atmosphere now, maybe more, especially in certain locations, polluted locations, than there were pre-industrially. So if you think about this pre-industrial atmosphere, there was water vapor, there were clouds forming, but a lot less particles. Particles are the seeds for cloud formation. So whenever we see a droplet or an ice crystal, that was formed on one of these pre-existing particles. And so that water was spread out over just a few particles. And so what does that mean? Every particle condensed a droplet, and those droplets were much larger. In a post-industrial modern atmosphere, a lot more particles, the same amount of water, but that means each of those droplets is a lot smaller nowadays. So what's the result? There's probably more clouds now, more particles scattered over the globe, much thicker, much more dense. It turns out that the white cloud on the right and the dark cloud on the left is actually accurate. Clouds with smaller droplets are brighter, they're whiter. So you can imagine a pre-industrial cloud being darker than a modern one, less clouds. And also those little droplets nowadays are less likely to precipitate. So the pre-industrial clouds probably precipitated out and dissipated much more quickly than they do now. And so all of these effects are leading towards an atmosphere with more clouds, more of that brightness, more scattering of sunlight back into space. Again, not something understood in the late 1800s. This is more of the modern studies that our group and others are doing that are trying to sort of really figure this out and describe this mechanism. So to start to try to wrap up, what I wanted to point out is that these Intergovernmental Panel on Climate Change reports really do a nice job of sort of summing these things up by category. And so one of the things that they've really figured out is that, CO2 has increased. We have this really good understanding of how greenhouse gases participate in our climate. You get this warming. It's well understood, so you have a very small error bar on here. On the other hand, the impact of particles and clouds is negative. It's not as big as the greenhouse gas warming, so the greenhouse gases are winning, but you're offsetting some percentage of it with particles and clouds. Not only that, but we don't understand particles and clouds as well as we understand greenhouse gases, which again, we've been studying for over 150 years. So the error bar is bigger on the effect of particles and clouds. And so if you go to the very bottom here, the total human effect, total anthropogenic effect, it's positive. The greenhouse gases are winning out, but the uncertainty on that effect from relatively small watts per meter squared, I'll explain this in just a few moments, 1.5 watts per meter squared, up to maybe 3 is really the uncertainty on particles and clouds, not on the greenhouse gases. Just to give the viewers some idea, by the way, those little Christmas tree bulbs we had as kids, those were about 1 watt. And so what we're saying is we're heating the Earth up now by about the same magnitude as putting one of those little Christmas tree bulbs on every square meter, approximately a square yard of the surface of the planet. That's how much warmer the planet, that's how much more energy we have in the Earth system now. And so the difference here on the low end is between one of those bulbs per square meter, per square yard, and about 3. So that's the uncertainty that we're playing around with right now. So again, to sort of just wrap up this section, the Cliff's Note version of what we're talking about is that I'd like to hammer home this idea that particles and clouds scatter sunlight, so they're actually a cooling impact on the planet because of human activities. The net effect of that is not as great as it is for CO2, so it offsets some amount of climate change. Not only that, but it's also the most uncertain part of the climate system, or one of the most uncertain parts now. And so this is really why there's a lot of modern research going on in this area, is to understand this so that we can really reduce those error bars and come up with more certainty, especially in our projections of the future.
Always wondered, because I thought there's more clouds.
Yeah.
There absolutely are. Yeah, I always find it fascinating, if you could jump in a time machine and go back in time, how much different the clouds look? How much different did the sunset look 200 or 300 years ago than it does now? Over a human lifetime, we don't really perceive these changes. But we don't also have, great pictures from the year 1700, none, in fact. But at some point in the future, maybe we'll be able to mine old pictures or something like that and understand this better.
I'm guessing we'll be able to, as much data that's out there now.
Yeah.
There's webcam in every city at least.
Right.
It's really true. Yeah. Unfortunately, we might have to wait a while until we can see the changes, but it is something that's coming scientifically. So, now that we've talked about, the history of climate, natural climate versus human affected climate, one of the things that we do want to talk about is the debate in climate science. And so I do not want this to be political. That's not the intention here at all. But I think that there's a commonly perceived thought that there's uncertainty in climate, that there's a debate going on and so on. There was a paper that just came out last week, in fact, that polled scientists, climate scientists, and came to the conclusion that 99.9% of climate scientists believe that climate change is happening and that there's a human impact on climate. And so, that's 2021. But is that really true historically? And the answer to that is that, for a long time now, not only scientists, but others were concerned with climate change. And so here is a volume that came out called Restoring the Quality of Our Environment. And this really had to do with climate change. And I'm going to show you some quotes from this and some of the impacts from this. But what I really want to point out here is that the date on this is November of 1965. And so this is a White House level climate change report in the Johnson administration. This was a bipartisan work. Keeling, who we talked about earlier, was one of the scientists brought in for this. A number of other famous scientists were brought in. There was no real politics involved. This was really a discussion of what the impact would be, not only on the planet, but on the United States specifically. And so one of the quotes in this starts out with, the climatic changes that may be produced by the increase in CO2 content could be deleterious from the point of view of human beings. And so you can see right away that this is a report, again, generated in the mid-1960s, came out in the mid-1960s. It's coming from these data that were being produced in the 1950s that already realized from these old papers that we talked about that an increase in CO2, especially if you weren't doing anything about it, was going to have a bad impact on society, that it was going to have impacts that we would need to consider. I often think that if you went back to 1965 and told these folks that in 2021, we would still have people saying that there was a debate going on, I think that they would have been absolutely floored by that. What's interesting is that this volume, this paper, is not only laying out the case that climate change is starting, but they're already thinking about solutions. And so I think maybe a lot of folks that are here today that are watching this, are thinking about, well, what can I do? It's quite interesting that our government was saying, what can we do, back in the 1960s? And so, I think a lot of the viewers know we should be conserving energy. We should be maintaining as fuel efficient cars or hybrid vehicles or electric vehicles as possible. We should be moving over to alternative energy sources that are not producing carbon dioxide, so-called non-carbon or non-fossil energy sources. And so this report, this quote, is the possibility of deliberately bringing about countervailing climatic changes, therefore need to be thoroughly explored. They're already thinking about this in the 1960s. What can we do? And so to start to sort of wrap up our conversation today, this is a much more modern report. And this is from 2015, so the mid-teens. And so I want to encourage everybody that there are things that we as individual citizens, or as groups, as families, as universities, as communities can do to minimize our impact on greenhouse gases, to really reduce those. But we should also be thinking about this in sort of a national sense and really a global sense about what we can do. Again, we hark back to that curve that I showed earlier from Susan Solomon's paper in 2010 about the impacts of CO2, we really have to ask ourselves if turning down the tap is enough. And the answer in some cases may not be yes. It may not be just a matter of turning the CO2 taps down to zero. It may actually be that we have to think about removing these greenhouse gases, predominantly CO2, from the atmosphere. So this idea of carbon dioxide removal, it can also be called sequestration, this idea of removal and then putting it somewhere that it doesn't get back into the Earth system, into the climate system. And that's what's meant by sequestration. And so this report really lays out these large scale projects. So again, I want to separate what we as individuals or we as small communities can do from what we would have to do in a national or a global sense. And this report really lays out what we can do nationally or globally. And so I'm just going to put up a couple of quotes here, and I want you to pay attention to the years that these quotes are. So this idea of deforestation, taking trees out of our Earth system, has a deleterious effect on climate. It allows more CO2 and actually directly puts more CO2 into the environment. That was really understood very early on. It had been worked out by the 1930s, not a modern debate point. The idea of what's called reforestation, putting those trees back where they were, or afforestation, putting trees in completely new areas, was worked out by no later than the 1970s. It was being discussed even long before then. This idea of actually just removing CO2 at the smokestack, again, is not something that we're just thinking of now. This was something that was really worked out and published on as early as the 1970s. So again, these are not sort of community efforts. We can plant a tree, but to think about a national strategy or global strategy for reforestation, afforestation, scrubbing CO2, these are large scale projects that we need to think about doing. We've already worked out the basics of them as long ago as the 1930s, 1970s, and so on. And so I just want to close by making sure that folks here don't think this is science fiction. It's actually science fact. And so this is a project in the North Atlantic off the Norwegian coast that is actively sequestering carbon. It's a little different than what we're talking about. What's going on here is that these are wells. They're extracting natural gas, but this is natural gas that has a high amount of CO2 in it. In past decades, what would have happened is that a process would have been used to separate the CO2 from the natural gas, and the CO2 would have been just let go into the atmosphere, thereby increasing CO2. The Norwegian government in this case said, no, you cannot do that. Because there's high CO2 there, you can't just simply separate those two and let the CO2 go. You have to remove the CO2, and then you have to sequester it. And so this is actually a win-win scenario. CO2 is separated in situ in this location, and then it is driven back down to the well. What does that do? It increases the well pressure. It actually helps improve the extraction of the natural gas, and it is simultaneously sequestered. It is not allowed into the Earth system. The physics behind this, the engineering behind this, can be used for CO2 that's collected from a variety of means from our atmosphere. And again, these are real pictures. This is not a digital image. This isn't something, a conception for the future. This is what's going on now. And so with that, I'd love to, sort of continue our discussion. I just wanted to throw up this image, which was something when we were developing some of these thoughts in this lecture. I had a chance to talk to popular science. And so as a kid growing up, I loved reading popular science. And so this is sort of the nerd in me was so excited to be able to work with popular science. And I talked about, producing clouds and this idea of particles. And they were asking me about myself, and I was talking about a personal interest in going canoeing and fishing and things like that, getting out in nature. And so they put together this little image of a cloud experiment that we talked about in a jar, and my personal interest in fishing and canoeing. And they used this on the article that we did in Popular Science. So it's become sort of my personal avatar. So I'll just stop there and see if there's anything that you two would like to talk about further today.
I do have one question. Something because we're using thermometers to measure things now, and yet the methods that we're getting for past data, and now you'd mentioned that, well, we use thermometers. Now we're using instrumentation. now. But are we comparing that to the methods we used before to help make sure that it was accurate what we were looking at before?
That's another great question, Stephen. Yeah, thank you. So yes, the answer is yes. And actually, it's actually very critical, because to develop those proxies, you need to be able to compare them to a measured temperature scale. So I think it goes one step further, which is not only do we continue into the modern day to compare things like, tree ring records that are being developed, as we speak right now, what was the tree ring last year or 2 years ago or 3 years ago, and making sure it compares in the way that we think it does. But to develop those records, we needed that overlap. We needed those tree rings at the same time as we had a temperature record, so that we could then sort of bootstrap our way backwards in time with the tree rings. And so it's a pretty cool story. Again, this idea of dendrochronology is way beyond the research that I do. I'm just fascinated by it. But, so say you had a temperature record next to a tree from 1880, when we had, modern thermometers, until the modern age. So you could do that, and you could correlate. And so you've cut that tree down now, and maybe that tree started growing in 1880. Well, now what you need to do is find some tree rings that span from, say, 1700 to 1900. So now you've got the temperature record, the initial tree ring record, and now you've got an older tree ring that goes back further. And now you can take another tree that goes even further back in time, and further back in time, and further back in time. And you might say, well, where are you finding these trees from that started growing in year 1000? And there's this fascinating sort of science and history behind this, where people take timbers out of things like old cathedrals, or old farms, where they know what year it was cut down in, or what year that cathedral was built in. And they're able to extract those timbers and then lay them over in this very precise fashion, often for specific regions. And so, you can think about the tree ring history of the United States only really going back to the 1500s, whereas in Europe, you can often find tree ring records that might go back much, much further into the past. The same thing that we're talking about is absolutely true of fossils, modern life forms being extrapolated into fossils and so on, and then working your way back.
So I just wanted to make sure that they were, still checking that, and not like going away and, oh no, we're checking it a new way. Have our, like they say, the new math.
Yeah, no, it's really cool stuff. And you can even think about, one step further, which is like, not only is it still being checked in the modern age, but, we're developing new instruments or higher capability instruments now. And so, now we're able to even start thinking about different measurements or higher accuracy measurements. Like maybe we go back and reanalyze that ice core, or we reanalyze those tree ring records. And now there's this new instrument that we don't even have. So we're developing new records that can be 800,000 years old. It's really, really, really interesting stuff. But it's absolutely, to answer your question, pinned to the modern age.
Perfect. Well, thank you. This was very informative. A lot of information here, and it's really, really cool, because this is the first time I've seen someone present the historical side of what we call climate change today. And so I really appreciate you taking time to do that.
Thank you both so much for having me. And as you can tell, this is certainly one of these things that it's not only the science that I do, but it's really a passion too, which is this idea of how do we look at history, how do we look at the past to understand the present and the future. And there's such fascinating stories here. Again, it's like a book with these characters, Arrhenius, Foote, Tyndall, and so on.
Thank you for listening to this episode of Science from the Experts from Purdue University Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.